now is to give you one or two examples. I'm going to start with the first one, and I think I'll do another one afterwards because this one is still not optimal. But examples of PCA in a more, excuse me, a more realistic context than the one we looked at before when we were looking at the hockey player database. So this is the data set that I discussed at the very beginning of the course on PCA when I said we would look at these fingerprint measurements. And so what we are going to do is go through this data set a little bit, and I'm going to show you how to do PCA on this, and as well how to do it using built-in functions in R. So the first thing is I will distribute, of course, this worksheet, but the data comes from the thing that I'm linking, and part of the aim of this course is to show you that there are many ways to do things, whatever it is that you decide to do. And so here I'm going to use a slightly different method for getting the data than what I've used up to now. So most of the time to this point, we've used read CSV. And here I'm going to do differently because actually it turns out that the data that I'm going to play with is distributed as an Excel spreadsheet. And this is quite common, and so it's actually quite useful to learn how to get data that way. So I am going to get the data here, and what I'm going to do, so I'm just uncommenting this once. This first function that I'm using is actually getting the file that is at this URL here, and it's saving it locally, so it will be in your Jupyter Hub directory, wherever you have installed, uploaded this file. And so it will download it there and save it as this name that I'm giving it because, okay, why not? And then I'm going to use this package called OpenXLSX for Excel. This is one of the extensions of Excel spreadsheets. And so I just need to use this function, read.xlsx, to read in a file. And I'll just point out, as indicated here, you probably will have to install this package before you actually run this code. And as always, I show you a little preview of the data by just showing the head. So you can see that there's a bunch of columns, 11 of them exactly. Participant number, gender, age, dominant hand, height, and so on. And by the way, you can see on the left of the video, this is the description we had in the slides. So first of all, these column names here are extremely unusable. They are going to be hard to deal with. And so the first thing I want to do is rename some of those columns to make it easier to deal with. The other thing that I'm going to drop is this participant number because I really don't care about the participant number. Okay. And so this is what I do here. I just keep columns to the number of columns. So I am getting, so these are the columns, and I'm getting rid just of this first one here. And then I'm renaming the columns using these names. Okay, so gender, age, handedness instead of dominant hand, and so on and so forth. Of course, contrary to the data on the hockey players, it's very difficult to plot this because there are 10 variables here. One of them The gender is of course easier because it's a binary variable here, but the others, it would be complicated to draw, okay, to plot. So I'm going to proceed as we have done so far. It's always I'm going to center the data. And I'm also, before I do that, if you go back to this data, you'll see that here I have variables where the age is NA. So this is something you typically want to get rid of because it's annoying. So the problem of missing data is really complicated. It's something that statisticians spend a lot of time dealing with, and people dealing with databases and so on also. Here, I have enough data that I can get rid of rows that would contain an NA measurement. Okay, so I do that by using this this nice little function here, which is going to return the index of rows. Well, it's going to return true for the index of rows that are complete. That means rows that do not contain any NA. And so all I'm doing here is, wait, I don't know if I have evaluated this. Oops, no, I had, and so I shouldn't evaluate twice, of course, because here I'm getting rid of one column, and if I do it a second time, I don't have enough names for the columns that I have. Okay, so to come back to this problem, so here I'm going to get rid, I'm only going to keep, let's put it the other way, I'm only going to keep the rows that are complete, so the rows without NA. And then I'm going to make the list of things I want to center and I will be playing with. And for this, I'm going to forget gender. All the others I'm going to keep. Okay, I'm going to play with. But so here, what I'm doing is I'm saying the columns that I want to center are the following. And then all I need to do is loop on these column names. And I'm going to, so instead of centering the data in place, what I'm going to do is I'm going to create a copy of the existing column, and that copy will have the suffix .c, and it will be the same column as the previous one, but centered. Okay, this way, if I need to do other things with the data, I still have the non-centered data accessible. And so all I need to do is create a new, this here, printf, is a command that those of you who have programmed in C or in languages that came after C, like Java or C++, etc., you will know this. Printf is a function that uses these formatting characters, they're called, and replace, so what's happening here, this is creating a chain of character where %s will be replaced by a string, and that string is C, where C is one of those values. So the first value of C will be age, and so new C will be age.c. Second value of C will be height, and so new C will be height.c, and so on and so forth. And what I'm doing is I'm now creating a new column in my data that has name whatever I assigned on that iteration, and the value of that data is simply the value minus the mean of the value. And okay, I've got rid of NAs, but just in case I'm keeping this NA here. It doesn't hurt, it's not going to change anything. And so once I've done that, I get the same table as before, except that you can see that I've added all these columns, which are the same as the ones before, except that they are now centered values of the columns we had before. Okay, centered around the mean for that particular column. Now we compute the covariance matrix, and again, I don't want to use the gender because it's binary, or I mean it's got finite number of values. In this particular case, it's binary, but I don't want to use that one. So all I need to do is I need to create my data. I create it as a matrix, okay, and I just select those columns that are in this list, this vector to center that I had before. So that means I'm going to create a matrix. Actually, this is not the two-centered one. Interesting. Let me modify this. So if I do this, what I'm using is the original columns, but I wanted the columns that are centered, so I can just do the same thing as before. So when I run this is going to take to center. It's going to create a vector that will have a chain of character. Maybe I will put this here just to show you quickly. When I do this, you see I'm creating variables that are now age.c, height.c, weight.c, etc. So because these are the columns that I want to pick. Okay, so when I do this, X is my non-square matrix of observations, and so I have my variables as columns and my rows are the different observations, exactly like we had here, but here I've only retained the values for the columns that are centered. Okay, and then S is the unbiased estimator of the covariance matrix, and I just get it by dividing by the number of rows in X minus 1 and multiplying the transpose of X times matrix times X. Okay, and so what I get is a covariance matrix that indicates how these columns vary with respect to one another. And remember that the main diagonal here is the variance. Now I compute the eigenvalues, and I did not remember that eigenvalues seem to come out in an ordered way in R. I didn't remember that this was a feature. It's good. It means that what I'm doing just below is probably not necessary, but it's a good practice to keep anyway, because if anybody ever changes the way things work, sorting something that's already sorted is not very expensive in terms of computations. Whereas the errors you would run into if you did not do it would probably be annoying. Okay, so these are my eigenvalues. I'm just plotting the just displaying the eigenvalues. Of course, I could show the vectors as well, but I'm not going to worry. Here again, I said we'll just order them. I'm going to add the singular values, which are simply the square roots of the eigenvalues. So I do that here. And now I'm going to do the process that is going to allow me to change the basis in which I'm now going to express the data. And to get this basis, I need to take the eigenvectors and transform the eigenvectors into an orthogonal matrix. Okay, so I take the matrix of eigenvectors and I transform that matrix into an orthogonal matrix, and to do that I'm using Gram-Schmidt. Okay, we did that the other day in a simpler example, but we can do it here. And just to check, it's always good to, when you're using especially an interpreted language like R or Python, etc., it's always good to check that things are working the way you expect them to work. And so here what I'm doing is I'm just checking. Remember, this matrix must be orthogonal. That means the columns are orthogonal to each other, and they're also normalized. And so here I'm just checking that the columns are normalized, and you can see that when I'm taking this cumulative sum of the squares in each columns, this is what I'm doing here, well, I get 1 everywhere. So we're good for that. And I could add, for example, I could check, I'm not going to do them for all, but I could check that GS of Q of the first times, times. If I remember well, if I do this, it does the inner product. I'm not sure. Let's see. Yes. Okay. So that inner product is 0. So we're good. Those two columns are orthogonal. Of course, we could do something that you did in a previous exercise, several assignments ago, when I was asking you to check 2 by 2 that everything was working. Well, you could do this here. I'm not going to do it, but it would take a minute. So we indeed have an orthogonal matrix. And to construct the new basis, it's quite simple. And here I'm going, so let's do it, and then afterwards I'll switch to something else. Okay, maybe I'll just move back for a while. So I need to make a change of basis matrix. I can do that using, so first I'm making an identity matrix. So I remind you that the command diag in R is quite versatile, probably a bit too much, I would say, in the sense that it allows you to either create, if you just use one argument, a number, then it creates the identity matrix of that size. Otherwise, you can also use diag of a matrix to extract the main diagonal, or you can use diag of a vector to make a matrix that has this vector as its diagonal entries. So you can do a lot of things with diag. I actually think it would be more clever to not do all of those things with diag, but never mind. And we create the augmented matrix by taking the matrix of the orthogonal matrix and putting identity on the right, and then we reduce row echelon form the matrix, and we extract the columns on the right hand side now, because the left hand side will have the identity matrix and the right hand side has the matrix of change of basis. And we would just obtain, should move this, we would just obtain the new coordinates for x by multiplying x by a transpose of the matrix. Okay, but what I'm going to do, and I mean, we'll come back a little bit on this, but I'm just here going to focus on the use of the PCA. And if you were using the PCA, if I'm not asking you in an exercise to actually do that yourself, like to come up with a code to do it, well, you would probably use a function, because of course there's functions to do that. And the function is this, this function here, prcomp. So I'm going to say that data.pca is prcomp of data, and once again, I shouldn't say to center, I should say to center in the same way as I did before. I could use, okay, let me point out, I could use both, because one thing you will see, actually, it doesn't, normally it shouldn't matter whether I'm using to center or this, but just for the principle, I'm going to use the same as I did before. But you can see that one of the arguments of a function that computes the PCA is actually whether you center the data. So you don't need to center the data. You can say afterwards that you want to center the data. And so when I run this, I can then get the summary indicates. So typically this is a very good command to know in R. It gives you a summary of whatever variable you have. And if it's a complicated variable that is produced by a function like this one, it will also give you more information as to the variable. And so what you can see here, what it's outputting when you do take just the summary, is the principal components, PC1 to PC8, the standard deviation of the data along that principal component, and then the proportion of the variance of the data that is represented by that principal component, that is carried by that principal component. And so you can see here that, for instance, the first principal component carries almost 88%, this is a proportion, 88% of the variance of the sample. The second carries 8.4%. So essentially with PC1 and PC2, you're explaining most of the variance of the sample. And they also show the cumulative proportion. Okay, so this allows you to know if you've taken 4, for example, principal components, then you're accounting for 99.4% of the variance of the sample. Let me just point out that that proportion of the variance is very simple to compute, because what you're using is, if you look at the singular values, I remind you that if you've centered things, the singular values are the variance of each of the along each of the principal components. So these principal components that I computed myself earlier on, before I used this function, should carry essentially the same amount of information. And of course, here something is, I have a problem with my this is happening because of I have a centering that happened somewhere and not somewhere else. I don't remember where I did that. Okay, never mind. In principle, when I distribute the file, this will be fixed. In principle, you should see the same values occurring. Yes, I think I didn't reevaluate then. When I did. Okay, let me see. Just by curiosity, I'm going to be missing something, I'm quite sure, but never mind. Let's see. No, I think it's still the same. Yes, okay. I'll figure this out and I don't know what's happening here. It was fine before. Okay, never mind. Because that's not the one we're using. We're using this one here, the result of using this. Maybe it's scale. Let me see. There's also a way of scaling. Yes, that looks closer. It's not quite the same, but you can see there's numerical imprecision happening, of course, but yes, this is an additional factor that you can pass to the function that computes the PCA. It's the scale. I won't get into what it means, but you can see that here I'm getting, it's not quite the same value, but it's comparable, okay? And these are where these things are coming from, with numerical imprecisions that seem to play a very big role here. Okay, So to come back to the PCA function in R, the PCA function gives you a bunch of results that you can see here. I'm not going to go into the detail. One thing that you can see is that it is giving you the rotation. So, and I'm going to show you a graph to explain this perhaps a little better. What you're seeing here is the rotation of the different, so is it the, of the different directions with respect to PC1, I believe. So you'll see an illustration in a second, because this is not very clear at this point. Now, I'm going to use a plot mechanism, and here actually it's interesting. This is something that you'll run into from time to time. The library DevTools is something that you will use when you want to develop your own libraries, essentially. And it is required for this command below here, which is to install from GitHub. Because the way packages work in R is that they are vetted in, essentially, the R distribution system. So when you do install package, this is because the package has been approved for distribution in the main distribution system. There are some packages that lag a bit behind, and this is the case of this one, for instance, where new development is taking place. And if you want to install the latest version, instead of using the R CRAN, it's called the Comprehensive R Archive Network. So if instead of using this, you want to use a more bleeding edge version, you would install from GitHub, and you can do it using this. Okay. And so this allows me to do a biplot, and let me show you this. So this is showing a much different from what I had before, which is interesting, but it looks much better as well. It's the scaling. Okay, I know. This is because I've added the scale equals true here. So what this is doing, it's doing a biplot. So you can see that here we get the standardized PC1 and standardized PC2. So that's by default. You can change it. And what it's doing is it's plotting all the values in the coordinate system that has just these two principal components. And the arrows that you're seeing is what the mean of the original values are if you plot them in, of the variables, if you plot them in this new coordinate system. So the x-axis is the axis of the first principal component. The y-axis is the axis for the second principal component. These are all the points. I've added that I wanted grouping by handedness. So remember, I kept the handedness, but I did not use it for classification. And so when I say group by handedness, what it does is it just makes different colors for the different groups. First remark, you can see there's a problem here because I have a group that is left lowercase and a group left uppercase, and the same for right. So we'll need to fix this. But so this is, let me explain those arrows now. You can see all of those arrows here. Height, remember this is the centered height, the finger height, the finger area, and the finger width. The fact that they're lying around the x-axis means that they are the main contributors to this principal component 1, okay? Because if you follow in that direction, you get your following principal component 1. And so all of those contribute to principal component 1. Those two here, the temperature and the of the finger and the age of the person, explain, well, I mean, they are contributors to PC2 mostly, okay? It's mostly vertical. And this one is somewhere in the middle, essentially, okay? So this is saying, like, if I want to explain these things, I can, these differences in that data set, I can focus on all these that go in the same direction, and essentially taking some linear combination of those is going to explain most of the variance actually in that direction, which is the one that carries the most variance. It carries 55% of the variance. And these other two are going to account for 15% of the variance. Okay, so this is a sort of reverse look at the problem, where we've done our principal component analysis, decomposition if you want, and now we're looking at, of the original variables, which contribute to these principal components. And I'll just, yes, I will remember that I was just pointing out that handedness, we could be thinking, oh, maybe there's something with handedness in this data set, so we're going to fix this by just making all of the data in the handedness column lowercase, and then plot again. So now I should have only two groups, indeed, left-handed and right-handed people. You see that they're a bit everywhere. This doesn't change. Of course, I'm just changing the way I'm representing the groups. One thing that you can do is you can make an ellipse that contains a normal distribution of the points. So it sort of gives you the bivariate normal. Don't worry about it. You know, like a paraboloid that's going like this, and it's plotting where most of those points are. And so this is what you get here. That's, in a way, what that shows you is that those two groups, the handedness doesn't really play a role. Those two ellipses are overlapping to a large extent, and so there's no real distinction. I hope that in the next example I'll do after this video, I will be able to show you something more probant, so that you can see some cases where these things would play a role.